change these. Five here would be. All right, got that done. Hey, Ben, I appreciate your patience there. I just had to make those grade adjustments we talked about in class. I got your email with your notes outline, and I'd like for us to go over it a little bit. If you could tell me just a bit, where is this? Where did that go? Unflag, delete. Where did those notes go? I know I saw them. Oh, they got bumped down. Okay.
Yeah, I had emailed them to you.
Yeah, I got them here somewhere. I restarted my mail client and got a bunch of stuff dumped on me. So where?
I got you.
This is from Friday. This is so strange. There they are. Okay, I flagged them. All right. So let me open these and I'll turn on my screen share. So we have here, we're going to talk about indefinite integrals, and they're both present in calculus established. Connecting between derivatives and definite integrals. Good. Yeah. And this is an antiderivative of f. Good. Part 2, this is found by evaluating this where capital F is an antiderivative. Good. The notion of an indefinite integral is given by this notation. Yeah. Good. So one little thing I would advise here is slapping a plus c at the end of this note right here. So you say, thus the integral of little f dx is equal to capital F, where capital F prime is little f.
Okay.
People so often forget the plus c. I wouldn't think about it as being a part of capital F. I would write it as a separate thing.
Of course. Yeah, for here, I was gonna explain like the importance of including plus c, along with evaluating like the antiderivative of f prime of x and y equals f of x. So then I was gonna go back in and explain if you take the derivative of the antiderivative, plus c could be any constant like +5 +4. So which is why you need to include it.
Good. Yeah, I think making a comment about that and explaining, yeah, this constant will always differentiate to 0. So this is really the general antiderivative. That's good. That's good.
Yeah. So wait, do you want me to go back and write the plus c, or is it fine if I just like make a verbal note of it when I'm presenting the topic?
I think it would still be wise to write it if we could.
Okay.
If you've got room, you can just squeeze it in there.
Of course.
So let me say there's a difference between this and this. For sure. Yeah, so this is a number, right? It represents area. This is sort of the most general antiderivative. Definite integrals result in numbers. Good. Well, indefinite integrals result in functions. And a little subtle thing here would be the same sort of thing is that the indefinite integral results in not just one function, but an infinite family of functions, right? Because of that plus c, we're talking about all the antiderivatives. So there might be a little note you could say here is that it's not really a particular function, but an infinite family of functions. So definite integrals result in numbers, while indefinite integrals result in infinite families of functions. That's a connection I would like to try and make.
Okay. Is this like meeting being recorded so I can view it afterwards as well? Because I'm taking
It
notes on
might be.
my.
I think it's recorded by default. Yeah, so I could send you a link for this afterwards.
Yes, please. Thank you.
All right. Answer everything derivative. Good. We can differentiate. Good. Important part of the indefinite integrals is a general table obtained from first. Good.
Oh, wait, and then here, which I can't really do it with the way I would be presenting. The page after this one, which would be page 4, is where I show the table. So before I move on, like past that little page squiggly line break thing, I would go. Yeah.
Okay,
yeah, I'd scroll down and like explain the table and, basically prove what I had just said at the top of page 3.
okay, yeah, that's fine, that's fine. And then an important note is that this is used only when we're given a function for its indefinite integral. We assume it is valid on the integral. Okay. For example, this guy is this, knowing that it's valid on the interval. Good. Yeah. Okay. So we want to be mindful of domains.
Yeah.
Um, Here we can write this as cosecant cotangent, and then according to our table. Good. We've got the power rule. Nice. So yeah, we want to take all those rules that we showed for antiderivatives, perfect, and re-express them in terms of the integral notation. This is good.
Yeah. And then I do some examples with individual rules. And then after I cover each 4 rules, I go into all of them combined, basically.
Good. I like it. This looks good.
Yeah.
Constant multiples.
And then here are those examples.
Nice. There's one thing I would like to add here. When we have,
Okay.
I think I mentioned in class A, when we have an integral that has multiple kind of pieces, like here, this has 3 pieces, we want to put the integrand in parentheses. It's something
Okay.
I want to kind of force everybody to do right now, because when we talk about u sub, the differential term is going to need to be like distributed or factored in that way. So if we could sneak some parens in here, I think that would be nice. And then
Of
everything
course.
else looks good. We'll split it up and the dx goes to each, and then each of these gets their little power rule thing.
Gotcha.
This one looks good. Don't forget your dx at the end of this integral here.
Okay.
And cosecant cotangent, same thing here. Let's put this in parentheses. So 3 cosecant cotangent minus 7 secant squared of x, as long as we have this whole thing in big parens, will be good. And then the next line is fine. And then here, a little note about the C1 and C2 kind of being combined into a single plus C. You don't have to write it, but just a verbal mention that, okay, yeah, each of these kind of comes with their own little constant, but because it's an arbitrary constant, we can combine them all into one.
Okay. Yeah, that's I did that
That's
for
like
notation sake to like
Yeah.
emphasize taking the integral of each individual function, and that individual function would put out a C1 that is combined into, arbitrary C.
That's good. That's good. I think that's perfect. We just need to tell people what we're doing as we do it. So as long as you have a little verbal comment there, that'll be good.
Gotcha.
And then here, we're going to do the same sort of thing. We're going to split this up. And okay, yeah, and those will cancel. And this will become secant theta, and that will become sine theta. That's good. Applications, FTCs like this. So this represents the rate of change. Yep. So this is like an average rate of change. Yeah. Then we can show that net change. Good. Yeah, very, very good. Okay. And then we have nice, a kinematics problem. Okay.
Yeah.
So this would be the net change in velocity.
Mhm.
And then we could find the net change in displacement similarly by integrating velocity. Good, 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 good. And this is a nice place to talk about the difference between displacement and distance traveled, right? Because if I'm going, in one direction and then in another direction, my velocity function is sometimes positive and sometimes negative, then the net change in displacement isn't necessarily the same as distance traveled. And because that's something we've alluded to in the past, I think it would be nice to mention here.
Like tie the end
So
up.
yeah, exactly. So you've got your part A where you're finding the displacement, you've got your part B where you're finding the distance traveled. And make sure you just explain the difference between these two kind of as we go through.
Gotcha. Will do. And
Oh,
then here I was gonna run through examples like kind of live in Paint 3D.
okay.
I don't have a document camera, so I wasn't like I was also gonna ask you, do you have any recommendations for how I could do that? Because I don't have a document camera like to record me writing on paper. So the
Yeah,
best thing that I could think of is just going into Paint 3D and sharing the screen.
if you are comfortable working in Paint, like if you have a drawing tablet and you're able to get good looking things there, that works.
Mhm.
What I've seen other people doing is using their cell phone as a document camera. So I think, who was it? We had 2 people do that, but I can't remember right now who it was. I think 2 of the girls, or Thomas did one, and then one of the girls did hers that way too. I think it was maybe Haley.
Mhm.
I think, yeah, I think Haley did hers that way also. So what she did is she like had her cell phone. She had like a stack of books, and then she kind of had her cell phone sitting with the camera poking over the edge, looking down on the paper she was writing on. And I was shocked
Oh,
at the
okay.
quality that gave. The focus was really nice. And that way she was able to use Zoom directly on her phone to sort of broadcast the document camera thing. Whatever you
Gotcha.
want to try to do, practice with it first. So if you're going
Okay.
to use Paint, just practice and make sure you can generate good looking things kind of live on the fly. Or if you wanted to try using the phone, talk to either Thomas or Haley, send them an email or a message on Canvas, letting them know that you're trying to do that and you'd like to know kind of how they did it and if they had any tips. I think that would be good. But the notes look
Understood.
wonderful. And is there anything you wanted to ask me about?
No. Well, I actually was going to do like a Microsoft slide kind of or a Microsoft PowerPoint presentation,
Mhm.
but I had a lot of trouble recording like the lecture through Zoom because whenever I would stop it and break it up into individual pieces, the recording would get replaced by the one that I just did.
Oh,
So
that's
I guess
frustrating.
the only question I would have is it okay if I like have it written out on the paper and I just talk through the notes that I have on paper?
I am okay with that. Yeah. One thing that might be useful for that is kind of an uncovering method. So if you have the notes on paper, if it's possible to kind of do something like this, where you go here and then here and then here,
Okay,
sort of reveal one line at a time, I think that can make it less intimidating for your classmates because they're like, okay, this is all I have to write right now. And
yeah,
then
yeah,
kind of give them time to write versus like splashing it all up at once can be like, okay, I need to quick copy this down. And then they're not thinking along with you as much.
for
So if there's
sure.
a way to do a kind of slow reveal like that, if you want to do that with the pre-written stuff, that's fine too.
Okay, so instead of a video, maybe I get like a blank sheet of paper and then take individual pictures of like the examples and then just keep sliding that paper down after I take one picture.
Yeah, that works. That
Okay,
works.
cool.
Yep. Just again, make sure you practice it. Make sure you practice it like on Zoom and that it's coming across well.
Of course.
Alrighty, is there anything else I can help with to help this go smooth or anything else we should talk about?
That's really it. I don't know if you could tell, but I was really panicking when I was sending you those emails. I wasn't
I
sure if it was
saw the,
Monday.
yeah, I did when
Yeah,
I just saw it on my phone this morning and I was like, oh no, he must be so worried, but I apologize, I didn't have time to get back to you.
yeah, no worries.
But yeah, it'll all be just fine and we'll do it on Wednesday. And just again, make sure you practice between now and then so the delivery is smooth. And if you run into any troubles, let me know, okay?
Sounds good. Thank you so much.
Of course. Take care, Ben.
Yep, thank you. You too.
All right, and Fabrice should be joining us. Hey, Fabrice, how's it going? Oh, I see. We're still waiting for audio connect. Alrighty, I got you there. How you doing, Fabrice?
Oh, I'm doing good. How you doing?
I'm good. I'm good. What can I help you with today?
On homework 10, right? I was trying to do number 1. I don't know. It felt like I graphed the graph right because I tried to graph the graph by myself,
Mhm.
and then I mean I didn't graph it right the first time I think, and then I tried to do it again and I think it's right, but when I was looking for the how you call it the R5.
Mhm.
I couldn't find like the answer. I would get like a negative number every time I tried it.
So this might end up being negative. That's entirely possible.
Right.
But if it was telling you that the answer is wrong, then probably it is. So let's take a look.
Because what I did is I said n equals 5, right? And
Mhm.
then I did what you do it b minus a over n, which is 4 plus 6, because it's negative 6, so 4 plus 6 over 5, which is 2. And after I did the xi, yeah, a plus I delta x with negative 6 plus 2i, right? And then now after I tried to plug in negative 6 for I and then kept on going like that down the line, and then but somehow
I see.
Okay.
So there is a little bit of an issue there here, and I'll walk you through this. The first x1 won't actually be -6 because we're using right endpoints. So we can think of this as a formula thing. We can think of it as a picture thing. And we'll kind of walk through it both ways here. So delta x, like you said, is b minus a over n. So here that's going to be 4 minus -6 over 5, which
Right.
is 10 over 5, which is
Just
2. And then the xi's, where do I do this? I'll do it here. Xi is always a plus I times delta x. And remember, this formula starts with x1, right? So it's f of x1 plus f of x2 plus f of x3. So our xi's here are going to be -6 plus I times 2.
Right.
So x1 is going to be -6 plus 2. x2 is going to be -6 plus 2 times 2 is 4. x3 would be -6 plus 3 times 2, which is 6. So this is -6 plus 6. x4 would be -6 plus 4 times 2, which is 8. And x5 would be -6 plus 5 times 2, which is 10. So x1 isn't actually going to be -6, it's going to be -4. -6 would be the left end point of that first subinterval. So it looks like you're kind of mixing up some.
Yeah, because what I did is on the x-axis, I took the point and plugged them in for I, which I
Let me see. So we can look at the picture too and make sure we've
Yeah.
got everything set up right. All right.
because it says from point -6 to 4, right?
Mhm.
So what I did is I took -6, plug it in for I, and after that -4, plug it in for I to,
So
I
the
did.
-6, the only things these are telling us, these actually don't tell us anything to do with the I values.
Right,
This is-
that's where I think I was like, I messed up.
I think so too. Yeah, that's what it sounds like. It sounds like that's the only real issue here. If we want to think of this from the picture, we can do that too, though. So this is a line with slope 1 and y-intercept -1. So he would look like this. So if this over here was like -6, and then -5, -4, I'm gonna have to break this up a little differently. We'll call this -6, -4. Fuck me, I don't really have space for it.
Yes, I get it.
But the idea is that, yeah, our first rectangle would actually be determined by the height at the right endpoint of the first subinterval. So that first rectangle, rather than coming down here, is actually going to be like here.
Which is -4.
Yes, exactly. Yep. So this would be -4. And so the way I would do this from here would really just be to use the recipe, the formula up here, because there's enough going on that it's difficult to have both in the same thing. But like we said, x1 is -4. So first we'll have f of -4. x2 is -2. So I'll have f of -2. And then f of 0. And then f of 2. And then f of 4.
Mhm.
And all of this will be multiplied by delta x, which we said was 2.
2.
So then we just have to plug in for our function. So what is f of x? It's x minus 1, right? So
Right.
this would be -4 minus 1 plus -2 minus 1 plus 0 minus 1 plus 2 minus 1 plus 4 minus 1 all times 2. And then from here, we can just clean up a little bit. -4 minus 1 is -5. -2 minus 1 is -3. 0 minus 1 is -1. 2 minus 1 is 1. And 4 minus 1 is 3. So all of this is getting multiplied by 2. And now we compute. So what do we have here? This is -8. These two add up to 0. So, and then we'll have -8 plus 3 is -5, right?
Yeah. So we go -10.
Yeah, perfect. And that's it. That should be our guy.
Now I see why I messed up because I was using the numbers between -6 and 4.
And I see how that
It's
could be
not A.
confusing. Yeah. But you're good with this formula. And then
Yeah.
just remember here that we always plug in I equals 0, 1, 2, 3 out to n. And that R's always start with x1 and L's always start with x0.
Yeah.
So kind of the first thing I do when I see a problem like this is write this formula down.
Mhm.
Once I have this formula, that kind of tells me what I'm gonna need. Okay, I need x1, x2, x3. So I'll cook up delta x, then cook up the formula for xi, and then I plug in whatever I need to get those xi's out. Does that feel a little more comfortable?
Yeah.
Cool, cool. I don't think there's anybody else here. So if you had another problem you wanted to look at or something like that, we could do that. Or if you just want to work on some stuff and holler when you get stuck, whatever you'd like to do is fine.
Yeah, I'll go ahead and work on some stuff, and then if I'm stuck. Oh yeah, one more thing. I almost forgot.
Yeah, what you got?
I think it was number 2. Because I'm still trying to get comfy with it was number 2
Okay.
with
So,
the
oops, sorry.
Yeah.
So they give us the table here and they say find upper and lower estimates for the integral from 10 to 30 of f of x dx. So first I would graph the points from this table. That would be my first step. So let's do that. We're going 10, 14, 18, 22. Going to, those run from 10 to 30 and the y values are mostly negative. So I'm going to come out here. I'll just call this 10. And then we've got 14, 18. It looks like these are all spaced 4 apart. So we'll draw the
Yeah.
equal widths 22, 26, 26, and 30. And then they say, okay, so f of x, when x is 10, f of x is -11. So I'll call this -11. So here's this point. And then when x is equal to 14, f of x is -8. Well, it's -8.
So one question, the lower estimate, is it L? Is it L?
That depends. It depends on whether the function is increasing or decreasing.
Okay.
And that's one of the reasons it's nice to look at the picture first. But if the function is increasing, then L will be the lower estimate and R will be the upper estimate. If the
Okay.
function is decreasing, then L will be the upper estimate and R will be the lower estimate.
Okay.
All right, at 22, we're at +1. So I'll try to mark that as being somewhat symmetric in height. And then 26, we're at 4. Getting bigger. And 30, we're up at 8. Somewhere like, I'll try to make it symmetric. Like this. So this curve is increasing everywhere, right? And maybe I don't know exactly what it looks like, but it looks to me something like this. And what they want is an estimate of the integral. Now, the exact integral would be this exact area. And we don't have enough information to find it because they haven't given me a formula for the function. But we can use the rectangles and Riemann sums to try and approximate. So that's what we'll do. I think if we use, so because this function is increasing everywhere, L will overestimate and R will underestimate. So because f of x is increasing on the interval 10 to 30, how many things do we have here? 1, 2, 3, 4, 5. L5 will, what's that going to do? Is that going to underestimate?
So 10 don't count.
R5.
You said L5.
Say that one more time.
Yeah, you said L5, so 10 doesn't count.
Well, you got to think about how many subintervals we have. So how many
Oh, yeah,
rectangles
right.
will we have?
Yeah.
So there's always
It's,
one
it's
next
not
to
it's not
one.
about the point, but it's about the space between them.
Exactly.
That's true.
Yep, perfect. So L5 would be like this is x0, x1, x2, x3, x4, and x5. So L5 would be f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4 all times delta x. And this will be an underestimate, right?
Right.
Because we're increasing. And that is f of 10 plus f of 14 plus f of 18 plus f of 22 plus f of 26. All times the width between any two of these is 4. So in L5, we don't use the last guy. We use the first few. And then in R5, it's going to be the other way around. We won't use the first guy, but we will use the last guy. So what was f of 10? That was negative 11 plus, and then negative 8 plus, what was the next one? F of 18, that's negative 1 plus f of 22 is positive 1 plus f of 26 is 4. And all of this is multiplied by 4. So then you could crunch this out. And then the same sort of thing for R5. R5 would be like f of, this time starting at x1, and we'll go all the way out to f of x5 plus f of x2 plus f of x3 plus f of x4, and then f of x5 all times delta x. And that would be f of x1 is 14 plus f of x2 is 18. And then f of x3 is 22. And then f of 26. And then f of 30. And then delta x here was 4 again. So then our last step is to plug in these y values. F of 14 is negative 8. F of 18 is negative 1. Plus f of 22 is positive 1. F of 26 was positive 4, and f of 30 was positive 8 times 4. So then we just have to crunch these two things out. This would be our overestimate. So these are a little bit tricky. I think starting by drawing the picture is the big thing. So from the table they give you, just plot those points. It doesn't have to be perfect. Like you see, mine isn't very pretty, but it gives us an idea of what we're looking at, and it helps us remember like which pieces go with which.
Right.
And then what you said was perfect. That's kind of the main sticking point, the idea that it's not really the points, but the space between the points that matters. That's the big observation that we need. So I'm really glad you noticed that. That's perfect.
Yeah, but I think I got it now. But I think one thing I wasn't able to understand was, what was it? Give me a minute.
Yeah, no worries. We got all the time in the world.
Yeah, it was about antiderivative, I couldn't really understand it. Like when we talk about it, I think it was when on last Friday. We
Yeah,
talked
that was
about
it. Yep, last Friday
Yeah.
was the antiderivative lecture, yeah. Which part was giving you a hard time?
I mean, I was fine, but after that, I went back to it. I feel like I didn't understand the whole section at all. I was trying, but I couldn't really get it.
So the basic idea,
One thing I think I was able to get is that it's like doing the inverse
yeah,
of things.
yeah, exactly. I say capital F is an antiderivative for little f if the derivative of big F is little f. So when you're trying to find an antiderivative, what you're looking for is a function whose derivative is the thing you are given. So like if I tell you little f of x is x cubed, I have to ask what function has derivative f primed of x equal to x cubed. And that's where our power rule comes in. So we know if I were to differentiate something, the power would go down by 1, and we'd also multiply by the old power. So if I want to go backwards in that, the power has to go up by 1, and I have to divide by the new power.
Right.
So the capital F that would work here is 1/4 x to the 4, because then f primed would be 1/4 times 4x cubed, and the 4's would cancel, and we get the original x cubed. That's kind of the idea. So for power functions, at least, it's not too bad. To find an antiderivative, you add 1 to the power, so the 3 becomes a 4, and then you divide by that new power. So in general,
Okay. I think this is how it feels. Feels like I get it, but at the same time, it feels confusing at the same time.
it's definitely hard. Antiderivatives are way harder than derivatives. But there's a few rules we have, and this power rule is the first one we need to get comfy with. So like if you start with x to some power and you want to find an antiderivative, you increase the power by 1 and then divide by that new power. So that's where the 1/4 x to the 4 came from. I add 1 to the 3 and then I divide by the new power. So practicing is what's going to make perfect here. I think I can probably find you some videos with extra examples that might help. Let me see. I really like the way Patrick JMT does these. And then another thing is kind of just making sure that you know the basic, yeah, here we go, integrals, antiderivatives. So let me send you these. These would be good if you get stuck or you're having trouble. Watch a few of these videos. These are really good. Oh, but here he's writing them as, maybe I can find one where he uses the other notation. No, he's not using that other notation yet here either. So we haven't talked about indefinite integrals. So we're not quite ready for the notation he's using. Derivatives. Let's see if I can find one that doesn't use the integral notation. Probably everything will. XTN. Yeah, here's some. This is not bad. Yeah, and it's got some step-by-step into. They're using the same notation there too. Unfortunately, we're in this kind of in-between place right now where I haven't shown you guys the notation we're gonna use for antiderivatives. So very soon, I'll send you this. Just be aware that the notation he's using, we will introduce soon. But you'll see him writing an integral here without any bounds. It's called an indefinite integral, and it's just another way to talk about antiderivatives. Let me see if this guy using that. Yeah, here's a better one. I would start with this one. So the one I just sent you, that's going to be a little bit hard to understand right now, but I think this one will be a little easier. So start with the second video.
Let me go ahead and copy that.
Yeah, he does a good job here. And then also, after you look at some of the homework problems, going back over the lecture video from Friday, which I think is up by now. I started uploading it this morning. That will also help. Let me make sure that that's up and working. I was worried that maybe I uploaded the wrong one. So let me see. This should be from the 26th, right? Yeah, this is it. All right. Yep. Okay. Yeah. So this one is definitely good too. This is our lecture from Friday, and rewatching that after you look at a few problems.
Mhm.
will help. So I'm going to hang out here. If you do run into any other questions or anything else you want to talk about, just let me know. Okay.
All right.
Yeah.